Happy Friday, everyone, and thank you for making the time to join Western Dredging Association today. And big thank you to Brian Abbott for making time to give us this presentation. Just a little rules engagement. Hopefully when you guys logged in, you did see the poll to take. So please do take the poll. We as an organization are trying to obtain better data, which will help us see how we can meet members' needs at a higher level. So we're really excited, again, to have the opportunity to offer educational opportunities to the Western Dredging Association members. And so we definitely want to get your feedback. Today we will be doing all Q&As. We're going to hold them to the end, but please don't hold your questions until the end. Feel free to chat them. I'll be monitoring the Q&A. Brian is, I've listened to the presentation just recently. It's extremely educational. So I'm really excited to see what types of questions we have that may or may not come in. So please do that. And Brian said that if we need to go over a couple minutes, he is willing to stay. So again, thank you, Brian, for all that you're doing for the Western Dredging Association. Please feel free to introduce yourself into the chat, your name, your company, maybe your location, just so people can see who's here. We had over 400 people register. And so we expect to have quite a bit of people here. We had somebody chat that they cannot hear me. So if you cannot hear me, maybe just restart your Zoom. That's my best guess. And I appreciate everybody chatting that they did hear me, because that would have been terribly terrible waste of time. So thank you guys for participating there. This webinar is being recorded, and the slides and the recording will be posted on the WEDA website for members to download at a later date. Again, thank you so much, Brian, for allowing us to do that. Brian Abbott has over 25 years of project management, underwater engineering inspections, hydrographic surveys, and acoustic imaging experience. Mr. Abbott is the owner of Abbott Underwater Acoustics, LLC, which works in the area of underwater inspection of marine structures. Mr. Abbott is also part-time employed by Kongsberg and Mesotech for special projects. This work includes, but is not limited to, training on Kongsberg Mesotech equipment, testing of new prototype equipment, homeland security projects, bridge, port, and harbor inspections, archaeological surveys, and includes educational courses on acoustic systems. I learned today that Brian has been on the Titanic. He has tracked Bigfoot in the Pacific Northwest. He's worked on some forensic scientist project, and he's also worked on searching for boats and alien vessels in waters based on clients' needs. So we're very excited to have him. Brian is also a survivor of 4 helicopter crashes while he was active duty in the United States Marine Corps. So thank you so much, Brian, and I will be turning it over to you. You're muted still, my friend. You are.
Okay.
There you go.
Can you hear me now?
Yes, sir.
All right. Well, thank you for the nice introduction. Yeah, I've gone down some really bad rabbit holes in my life, so it's kind of interesting. But I guess let's just get rolling with the program. All right. So I'm going to make sure that we start from the beginning here. And can everybody see this screen fine?
No, I see your picture still. So why don't you hit that share screen button? It might have kicked you out. There you
Okay. Share. Try that. All right.
Yep.
All right. Can people see this now?
Yes, sir.
All right. So, well, good morning, good afternoon, wherever you may be in the world. Thank you for dropping by and learning about this. This is going to be kind of an intense flyby of underwater acoustic systems. I say this is going to be, 30 pounds of crap in a 2-pound bag, because we can't get into any details. I just want to make you aware of the systems that are out there, that how you use them for specific jobs to get the best information or data set that you can get. Like I said, I've been working in this area for a few years now. Been underwater inspections of structures, bridges, dams, ports, and harbors, done a ton of archaeological stuff. I also do POW MIA work around the world, looking at generally World War II battlefields, looking for planes, looking for landing craft vehicles in the Pacific, or tanks that have been lost. So I have been around the world quite a bit and have enjoyed my travels doing that. So having said that, this is me. I used to do a lot of commercial diving. As I got old and bald, I decided not to do it anymore. It's pretty much a young boy's game. But this is looking at bridge piers right here, carrying the POW MIA flag. I'm on the little harbor of Tarawa, looking for lost landing craft vehicles or other vehicles from the Battle of Tarawa in 1943. So here we go. So let's start. Your toolbox. As everyone says, you don't pull out a crescent wrench and go pound screws in. You need the right tool for the right job. And what is that tool? But before we get into that, what we need to do, I think, is really critically important in my years and experience, is what is it you're trying to resolve? What is it you're looking for as an end product? What are you trying to deliver to your client? What does your client need? And that could be a baseline survey, just finding out what's down there, what's in there, what's it all about. The other thing I think it's really important too is, what is the smallest target you need to resolve? Are you looking for a massive ship that went down? Or are you looking for Bubba's handgun he threw over the side of a bridge pier? So it's a lot different in target size and shape, and we can get into a lot more things. But Other things, QA, QC, if there's an ongoing construction project underwater, they're driving sheet pile, whatever it may be, can you inspect that underwater and get an idea of what's happening? Are the sheets being driven properly and haven't split or gone outside of their boundaries and so forth? We can do that. Structural integrity. America's infrastructure is old. It has a lot of problems, a lot of issues. And inspecting that underwater, I think, is a critical component. Damage assessment. Have a ship collided with a dock or a bridge pier? We can go out and assess that damage. Is it out of alignment? Is it not closing or operating properly? Then we also have pre and post assessments. If you have a project and you need to cut like 700 sheet piles and you want to make sure you cut them down to the mud line, we can come in and do a pre-assessment of that, then come back and do a post-assessment of that fairly rapidly. And the other term is we have short-term and long-term monitoring. So if we have ongoing issues such as prop wash scour along a dock or along a bridge pier, that ships going and going, we can come in and monitor that both in a short-term time or a yearly time. So it all depends on what you're looking for. Sonars, here we go. Sound, navigation, and range. It's an acronym. That's what sonar stands for. And all sonars do is they measure echoes in time. So we send out a pulse and it reflects off something and comes back. And we'll talk about that for a moment. But they come in all different shapes and sizes, and they all have different capabilities, but they all send out an acoustic pulse into the water column. So how does it work? Very simplistically, we're going to talk about there's a special piece of material called piezoelectric, and it has the ability to hit with electricity. Once we hit that with electricity, we cause that crystal to vibrate. That vibration can then be directed and put out into the water column as an acoustic pulse or mechanical energy. That energy travels through the water column until it hits something and gets reflected back. So on this drawing here, it gets reflected off a diver, gets sent back to the transducer that we're using, gets picked up, sent up the sonar cable, goes through the power supply, back to the laptop computer. And the magic of our software, we can see an image or we can collect a 3D data point. It all depends on what the transducer's design and capabilities are. But that's generally what we do. We send a pulse through the water, it hits something, gets reflected back. We pick that up, send it back up to the computer, and we see an image or a data point. There are other components I think are critical to understanding getting good data. And obviously, computer, you need a power supply. And also, there are three other elements I think are really critically important. And in today's world, we'll talk about this a little bit more, but positioning I think is really important. And you also need heading and time. And these three things allow us to be accurate to probably 2 to 3 centimeters and where we're doing. Now, people are using their cell phone out there today. They can download an app and you can be within 50 feet of something, maybe 25 feet, depending on the application. So it's important though, but when you're dealing with structural issues, you need to be close to looking at things from probably centimeter accuracy to make sure that you're getting a good position on everything. The next piece of equipment is really important, I think, is called a motion reference unit or an MRU. As if we've all been on boats, or if you've been on a boat will heave, rock, and roll, and so forth. Well, if we're shooting an acoustic pulse down, that pulse is going to travel straight down. But if the boat starts to rock, it's going to go off in that rocking direction or counter rocking direction. And so it's going to be deeper than what we think it is. So this motion reference unit will compensate for that. And it's really important when you start getting into the higher end sonars like multi-beam, especially profiling multi-beams. Another important piece of equipment is right here. It's called the sound speed, but it's a sound velocity probe. And one of the things that we need to do in almost all sonars is measure our speed of sound. And our speed of sound is dictated by three things. We have the temperature of the water, the depth of the water, and the salinity. If you're working in an environment that has a lot of tidal event areas, a 2-vector flow problem, where tides are coming and going, you're bringing in salt water, then the tide goes back out, and then the river starts to flow again, or the bay starts to flow again, it's bringing more fresh water in. This can change your speed of sound. It's a scalar factor thing, but it can really change the way that image looks or your data point looks. But this sound velocity probe will manage that for you and be able to compensate for the changes in water temperature, depth, or salinity that you work through. Now let's get into the equipment. The basic sonar tool that's out there in the world today is you can walk into Bass Pro Shop and you can hit the button and stick the flashlight in the water and you get a depth. But if we're working with that and we get a depth reading of 95 feet, what does that mean? That we have a depth from the transducer down to 95 feet. But if we have a GPS, that can give us an X and a Y position now, depending on the quality of the GPS. And one of the things that we need to worry about acoustically with all acoustic sonar sensors is that they all have a beam angle. So as the sound pulse travels from the transducer down to the bottom of the seabed, lake bed, riverbed, it's going to be an area of coverage. So it's called an acoustic footprint. And it's going to hit the bottom and get reflected back and picked up, and it's going to give us our depth reading. But we need to be able to understand our acoustic footprint, because on our next slide here, we're going to see a ship with a single beam echo sounder on it, and we're going to see different pathways that have taken across the seafloor here in the schematic drawing. We see that we've got a little bit of overlap, but if we notice this pathway here, we have gaps in our data. And this is the downside of single beam echo sounders, that we may have gaps in the beam traveling down in the size of our acoustic footprint, depending, especially in shallow water. So we're looking at this huge, area of non-coverage also, that is area versus coverage. So it's kind of the downside. We can compensate for that by getting higher end echo sounders that can be attached with motion reference units, with GPS RTK systems. We have one here set up with the base station. We're doing, at this job, we're doing river cross-sectional cuts for a new pipeline that was going in. So we needed to be very accurate, probably within 2 to 3 centimeters of where this pipeline was going to go. And we get this data, we can get complete coverage of the bottom and get the information that our client or contractor may need for the project. The next piece of equipment is probably one of the oldest out there. It was the workhorse of the industry. It probably still is in a lot of ways. A lot of people have them. They're phenomenal tools. They've been around forever. So they've been troubleshooted and people know what's right, what's wrong with them and stuff. And they come in all kind of different shapes and sizes and abilities and stuff. You don't see these too much anymore, but we have a single fixed frequency or single beam, they call sometimes. It may be like 330 kilohertz, and that's all it does. It shoots out 330 kilohertz of frequency, and it travels through the water column, reflects the bottom, gets sent back. Later on, they developed dual frequencies where you could do, say, a 330 and a 600 kilohertz, but you could only do one or the other at the time. Then they developed simultaneous dual frequencies. You'll see this a lot in today's world. If you've ever run side scan, you'll have a waterfall coming down the screen, and you'll have a split screen where 2 waterfalls. One might be a 600 kilohertz and the other may be a 900 kilohertz image of showing what's the bottom is. Now, the reason they show you 2 different frequencies is that with acoustics, there's a game that you play. It's called range versus resolution. The higher frequencies, like 800, 900 kilohertz, you get phenomenal data, better resolution than you do with the lower frequencies. But the downfall with higher frequencies is they can't travel as far out. Lower frequencies can travel farther, but they don't have the resolution that you need. So you play this game that's going on, a range versus resolution. Then we have another type of system called interferometric / bathymetric. This is a side scan that can take imaging data and also bathymetric data at the same time. So it's a unique system. It can cover kind of like 2 birds with 1 stone. So it's a really unique system and does a really nice job. One of the things that you're going to hear in today's acoustic world is chirp. There's some other things out there that are SAS and so forth. We're not going to get into today, but chirp, as you can see, stands for compressed high intensity radar pulse. And really, to all intents and purposes, for acoustic purposes, chirp takes different frequencies and sweeps through them as it sends out sound pulses. So you may go from, 5 kilohertz up to 20 kilohertz in a sub-bottom profiler, or it may go back down from 20 to 5. You go through these different frequencies to obtain better information, better data, maybe better analysis of what you have. So side scan, it's, like I said, it's been around forever. Gentleman here is ready to launch a side scan over the side. It's a towed system, meaning you have a cable. The downside to side scan, in my opinion, are two things. One is your cable length. So if you're working in 400 feet, or let's just say 100 feet of water, you're going to need 400 feet of cable. So it's a 1-to-4 ratio that you have trying to get that side scan down to the proper depth it needs. And I take my hat off to these men back in the day. They used to work in 10, 15,000 feet of water pulling side scan. And so when you look at that, you're looking at 50, 60, 70,000 feet of cable trying to get that down to the bottom. And you just don't turn the boat around and come back. So there was a lot of gamesmanship played in running side scan in this thing. And probably the most important thing about side scan is not the equipment, it's the boat driver. If you can get a great captain to run a boat, he's going to be able to run a straight line, because if he's not running a straight line, he's going to be all over the place. Your data is not going to amount to anything. So it's extremely important to have a good crew to be able to run straight lines to make sure that you keep that sonar towards the bottom and not running into the bottom or running into the side of something. On the right here, we have a picture of a chirp 900 kilohertz side scan from EdgeTech. It shows, obviously this looks like a shipwreck to me. We're able to see a beautiful image of the shipwreck on bottom. We've towed it right over the shipwreck, and we have a gap in here. This is called a nadir. It's a lack of signal that we get. So we'll talk about that in a moment here, but this shows a really nice layout of the ship. You can see the sides of the hull and the frames that are laying on bottom, some debris, maybe the engine. Not sure which is the bow or the stern, but just shows you what is going on with a really good side scan, a good boat captain to be able to drive over this. The other thing that we can do with side scan is we can run it. It's called mowing the grass or mowing the lawn. We can run things up and down or left or right, north or south. Then we can run these lines and we can overlap them together, and we can build what is called a mosaic. So we can take a large area, 3 by 5 mile area, and put it together as a mosaic and see what's down there. We can look for debris. We can look for geological features. We can look for, lost vehicles, lost ships, whatever it may be, and do that. So we get a large area of coverage. We get some detail, but we're able to see these types of things that are on bottom. So we get a nice layout of what's going on. The next area that we'll talk about is sub-bottom profilers. Sub-bottom profilers are a piece of acoustic equipment that can penetrate the ground or the lake bed, the seabed, the riverbed, whatever. They come in different capacities as far as pinger systems, bubbler systems, boomers, parametric, and here's our friend again, chirp. And as you see on the boat right here, this is a fair size shape. It weighs a couple 100 pounds, but it's a towed system. You tow it in the water. So there's both towed, but we can also go to an over the side mount system where we can run a different type of a piece of equipment to lower it over the side, put it on a pole system. We put our GPS on top. We have our X and Y. We measure the depth in the water. We have our Z value. So we have an X and a Y and a Z. We know where we're at. This is some of the data that you may get off sub-bottom. We'll show a little bit more of that. But if you look here, we have the lake bed that's right through here. This is the mud that's underneath here. So we have this kind of sediment load that's taking place here. But if we look here and we look here, we have the possibility of buried artifacts or pipelines or debris, whatever it may be. Down here, I believe this is just a reflection off the surface, exaggerated a little bit. But if you're going out to dig things up, you're going out to dredge them, it may be an idea that you might want to think about running sub-bottom just to see what possibly is down there, because You know, some of these harbors are old. They've been around for 200, 300, 400 years. You go over to Europe, they're 1,000 years. People may have been dumping stuff, trash, concrete slabs, whatever that you could be running into. So this gives you an idea of what's there. The other area is looking at geological features. This is the Baltic Sea. This is the seafloor down here that comes across. But if you look here, we have a discontinuity. What this discontinuity right here is bedrock, and we have it over here. So this is only a few feet, and we're going to hit bedrock. So if you're out there to dredge, you're out there to lay a pipeline, a new cable system, and bury it, you got to be aware of this, because you hit rock, the game changes and so forth. And this gives you an idea of what you have. You may have to move it over into this area. This area is a little different. I believe the rock sinks down into this area here. But if you notice here, I've got a parabola, right? When you come across targets underwater, like pipelines, buried targets, cables, and so forth, they're going to send this parabola signal. And this could be our buried target right here. We might have another one right here. And this is right under the surface here. Now in the Baltic, you don't know what you're going to get. This could be buried munitions. This could be buried bombs. It could be, you know, somebody's boat. Who knows? But you're able to see this and make arrangements like, okay, maybe we need to move over to a different position to look at this rock outcrop here. So this may be gas vents coming up through the bottom too. We're showing this. We'll see that here in a little bit. More sub-bottom data. This is a kind of cross-sectional cut showing the side of a slope that's underwater. You can see that there's been a slope failure. This area has come sliding down. Whoops, I apologize for that. Into the canyon here. And so if you're going to go out and you're going to dig for a pipeline, do a geological analysis and stuff like this, are you going to want to put something there? Are you going to want to dig something there? Because if you start digging or burying things, this could be slid down and buried deeper or destroy it or break it. The same thing is kind of here over in this direction too. We've got different depositional lines here. They're stratigraphy of sediment, and they could be sands, they could be silts, they could be clays. We just don't know. But you can see the buildup that's come through this bulge right here. This right here is possibly a gas leak that's being pushed up through the surface. And you can see it's not giving a really good reflection down here. But you go and you dig in through this, or you excavate through this, or bore this out, you're going to have gas coming up through the water column. That could be a bad day for some people. So just to let you know that this is what this can do for you to bring this together. Now, with this slide, even though my first degree was in geophysics, what I am a big proponent of is that, you know, I can show you those geophysical data, sedimentary logs and so forth, but I think they may be this, I think they may be that. I don't know for sure. I can't be 100%. So what I would recommend is you go out and take core samples. If you're going to go down 10 feet, go out and take some core samples to 10 feet to know what you're going to be drilling through, to make sure that you're not going to hit rock, to make sure that you're not going to go through a concrete slab that somebody dumped back there in the 1950s, or maybe even ammunition, you know, that from World War II, World War I, who knows. But I think it's a really good correlation to give you what you have and so forth underneath the water. The next area that we'll talk about is multi-beams. I've broken these down into two types. I'm going to call them a profiling multi-beam and an imaging multi-beam. And profiling multi-beams, all they do is take data points. So we have an X and a Y and a Z, we collect a data point. And then we have an imaging multi-beam, which just takes images, or we have a combination of both, and we'll show that. So here's a couple of pictures of profiling multi-beams. This is a Kongsberg EM 3002. We've got a MRU unit on this. We have a sound velocity probe. One of the things that I think that we should talk about too real quickly is that this is a sonar mount that actually keeps the sonar very stable in the position when it goes into the water as you're driving the boat. We don't want it vibrating. We don't want it, you know, moving around, because that's going to mess with your sonar data. Even though we have compensation for that, it's better to keep it rock solid. And on the right here, we have another Kongsberg multi-beam. It's called a 2040P. We have a MRU unit that's right here. And on the backside here, we have the sound velocity probe that we'll need. This blows me away at times. It never ceases to amaze me, but some of the data that can be collected and processed and put together and stuff like this, to me, it's not even sonar data. To me, I find this artwork. You can see the ripples. It's a large area. You can see the path that the sonar took going this direction or this direction, but you just get a great layout of the bottom. What are the problems? What are the positions? If these dunes are 3-4 feet high, if you're going to dredge that, it means a lot more sediment to dredge in the valleys, in the hills than in the valleys and so forth. And how do you compensate for that? On the left here, I worked in bridges for years, still do, but we have a Google Earth shot and an overlay of a multi-beam record showing the riverbed. And we can see the different bridge piers that go across through here. Well, if we notice here, the water flows from the bottom up to the top. And these areas are deep blue, are areas where the river has flowed in a higher velocity and able to pick up the sediments or particles, and it's called scour, and move it out of the way. So it could be moving in and exposing these piers. This one looks like it's getting pretty close. This one looks like it's going through there. And it gets a higher flow because what we've done with the bridge is that we've built it across the river and we've squeezed the river down. So when you squeeze waters, it's non-compressible, so it's going to flow faster. And we're able to pick up the speed, but now we can come back and measure that. We have an idea of the volume. We can come up with counter protection for that bridge pier to keep it safe and not have major issues or possibly even collapse. This is called an M3 sonar, high frequency. I'm going to play this and talk, but this has both. This has imaging capabilities and profiling capabilities. Right here, we have a cross-sectional cut. So here's our seafloor that's right here. Here's our pipeline. We're collecting 3-point cloud data that we can see the pipeline. We see the saddle weights on it. We have an X and a Y direction. But on the right here, we also have the ability to image it. So we're seeing an image of the saddles and the pipe and any other issues. And this is probably the best of both worlds, that you get the cloud point data and you get the imaging data. And you can really get some phenomenal data for your client and bring it in to see if there are problems or breaks or scour issues with this. All right. You can turn the sonar, the M3, on its side, and you can go along and, those of you that have been in America's infrastructure long enough to know that it's not in the best physical shape, but we can take images of the side and we can see what this sheet wall is doing. We can look down here. We might have a hole or a cut with something sticking in there. We might have a weight on the side of the sheet wall. We can see what the bottom looks like. If I was to guess, these might be zebra mussels that are on the sheet wall. And we're looking at a phenomenal record, just showing you that for the most part, the sheet wall is in pretty good shape. But if it's had structural damage, we can go in and assess that and look at that. Another piece of kit that is out there is called the Flex View. It is a shallow water type multi-beam system for imaging capabilities. And I think the best way to do this is just to go play this. This will take about a minute, but I just wanted to show you what this can do. This will take imaging data and they develop a post-processing capabilities that as you see this, will be post-processing the data live. So here comes the boat or the vessel, whatever you're using. We're coming in, we're looking at this intake here. We'll see the pipelines, we'll come in and see the shorelines here. And I'm just going to let this sit back and play, take a look at it, and I'll explain as we go along. So it's come in, it's taken in the dock structure. These are the pipes that are coming back from the dock structure where they can connect up. But now if you look here at the bottom, this isn't moving, this is stable. This will be our mosaic that this is being put together. So this is being done in, I don't want to say absolute real time, but there's a little bit of latency, but you're able to get this type of data and information. So here it comes. Here's our dock structure. We can see the pipes coming in. Now we look at another part of the dock structure coming up over in here, but now we start to see the shoreline coming up. So if there's shoreline failures or riprap failures of the shoreline, we're able to come in and look at that and assess that. And this has not been sped up. This has not been changed in speed at all. So you're able to do this pretty much in real time. Okay. Here's another one. This is the M3 coming back, but we're able to take, swath cuts of everything. This one's different. I'm just going to start to play it. This one shows an autonomous boat, and it's going along these piles here, and it's able to image these piles. We'll talk about this, but these autonomous boats are kind of a little bit of a game changer in the whole industry, because everything we've talked about, you can put on this autonomous boat. You don't need a big boat with a crew, a boat driver and stuff. You can pre-program it and send this out to do the job. It travels probably 3, maybe 5 knots, depending on what you're wanting to do capability-wise. So we're just able to look at this and come in and see on the collection of this data here that it's picking up right now. But then we're able to build a mosaic of that. This is one of my favorite pieces of equipment. This is called the dual axis, or DAS. This is what I call it, the ugly duckling. This is a beast. It's not pretty. It's not flashy at all. But if you need to do long-term monitoring, and it needs to be in a stable condition, but if you want to mount this in a harbor, you want to mount this next to a bridge pier to look for issues and problems, this is the tool to do that. This instrument it weighs 50 pounds roughly. It's heavy. It can take a hit from a log, from a possible boat, depending on the size of the vessel, but it's made to take a beating. And this is what I love about it. This was in Vancouver Harbor for roughly a little less than a year. I think it was 11 months, and it's loaded with, life on board, but it still worked. So we could put it in that position, leave it there for a time period. Here it is in a different boat, showing it nice and clean, ready to go. It's on a pole mount system. What we can do with this system is that we can set this in place on a sheet wall, on a bridge pier, and we can set it up so it can run every hour, every 5 hours, every time there's a huge event. We can run it 24/7. It's all. And what you want is a client to go out and manage that. And why is that important? Well, if we look here, this is DAS data. It's 3D cloud point. You can see out on the outer edge here, this is a sheet pile wall. This down here is the mud line. But if you notice, this is deeper over here than it is here. So what this is happening here is there's a vessel that comes and it parks its stern or its rear end over here. When it starts its props up, it kicks up the sediment here and pushes it all over to this side. All right. So we have 2 things going on that need to be monitored. Is this going to undermine the sheeting that's here? Because this is very old. And if another vessel comes in here to moor that doesn't have the draft that is over here, is it going to run into this? Is it going to have a problem? Is it going to get stuck? Is there anything else that could go wrong? So we can do this, like I said, 24/7, once a week, once a day, once every 2-3 hours. That's what I love about it. But it's got to be stable. It has to be kept from non-moving. We talked about this briefly, but one of the changes in the industry is that all the components we talked about can be put on these different types of autonomous vehicles. They're fantastic. They're very good at what they do. They can get the positioning. They can get the motion reference units, sound velocity probes. You can put the multi-beams on them, sub-bottom profilers, and you can send them out into harbor. The 2 downsides to these things is that it's not so much them as it is environmental issues. If you've got Bubba and Bert and Ernie out in their cigar boat, they don't know what this is. they may run into it, because this is on a set path. This is not going to deviate, not going to change. It's just going to go its direction. The other issue with the smaller boats that I've seen is that when you start getting into larger waves, probably greater than 2 to 3 meters, these smaller vessels can be overturned, and it becomes very difficult to get data and information. So this is really unique and really cool. You can Wi-Fi the data to you from the shore and just collect it, send it on its mission, and go, for several hours, bring it back, recharge batteries, send it back out. So it's a really game changer in the world. We're all moving towards more autonomous things, as we've seen with aerial drones. The last piece of kit is a precision type tool. It's called an MS-1000 sector scan. It is, if you want detail, if you want to know what's going on with your structure, this is the tool that you would need for that type of information. This is downtown Portland, Oregon, on a seawall on the Willamette River, done many years ago, but you can see that it's built on a wooden crib structure below the waterline. We have outfall pipes. You would look at the sediment here. These outfall pipes appear to be still active and being used. We have a very old one over here that nobody really knew about. It doesn't appear to be active, but it's a pretty big hole. The reason I consider it old, it's all built out of brick. It's got an arch instead of complete oval around it. So it just shows you some of the details that you can get from this type of acoustic system. Bridges. We're able to look at a bridge in the vertical position to see what's going on with it. This one right here, this would be a QA concern, a problem. This had a huge scour issue, and we designed riprap to be placed around the bridge to protect it from more scour. But what happened was that the contractor went out and just dumped his stone in a pile. We have a pile here and a pile there, and we have it was only supposed to be as high as this Tremiseal line that's right here. The reason being this is such a critical issue is this is a pathway for 1,000-foot vessels going right by this bridge pier. This bridge opens up, it's a lift bridge. And if this would collide with this rock pile or whatever, who knows what damage could be done to the vessel, let alone the bridge. So that's something it can do. Like Catherine mentioned in the beginning, shipwrecks. I'm a big fan of shipwrecks. I do a lot of work with them. This shows the detail that you can get with the shipwreck. We can see the frame systems and components. There's the old engine. This happens to be a blockade runner from the Confederate side. It was coming from Bermuda to North Carolina, and I believe it sunk in 1863. It's called the Agnes Fry. It was just uncovered a year or two ago. Not a year or two, 10, 12 years ago. And it was in sand. It's not that far off the beach. They were dredging the beach and they hit that. So knowing you're going to get yourself into, I think is critically important. And this will give you dimensions that you can measure and look at the size and shape. Ports and harbors. This is, getting back to what we talked about. What is it you need as a deliverable product? This could be a baseline survey. We know what's on bottom. We see everything from, roughly 250 feet out. We mosaic together. We can catalog everything that's on bottom. So this can be a homeland security issue. If there's a naval vessel coming into port, wants to moor there for a week or two, we can make sure that everything is clean and nice and nothing bad going to happen on the bottom that would hurt the ship or hurt the crew. So there's a lot of different things this data can be used for, but we get the detail to see that. This is just a real short 30-foot scan. 30 feet means from this center point to this outer edge of the circle, but you just get to see some of the details. You can measure frames. You can see boxes. We can see pipes and everything. We get to see sand dunes. So we get an idea of what the data is on a really nice point of view in what the deliverable end product might be for a potential client if they need to see this type of data. Here again, this is a side scan image. Now, the reason this isn't as great is because this is extremely shallow. This is about 12 feet. And the surf was really running that day. So we had a lot of waves, a lot of cavitation in the water column. So we didn't get the detail image, but we got a layout of the ship. We see what was going on with the ship. We can see that it's a mess. It's been beat up over the years and so forth. But when we can come in and change a piece of equipment, we can use an MS-1000, we can drop it around it and build a mosaic from that and get better detail for what we might need as we come across in this. All right. Again, GPS systems, I think, are critically important, especially if you're using hydrographic surveys, to have, maybe a CPath 130. Leica makes some not underwater, but navigational stuff or offshore. Leica is a high-end precision GPS RTK system that can be used on rivers and lakes and so forth around the country. Just about ready to wrap it up here. Kind of my last slide is that I am part of adjunct faculty at Northwest Michigan College. If you're interested in learning more about this, there's some phenomenal teachers there. I have a couple other partners in crime, Mark Atherton and Dan Vasey, that also help teach at the college. I don't think there's a better school in the world where you can go and learn what we just kind of talked about. And one of the things we haven't talked about at all is post-processing of the data. How do you give your client a deliverable report that's useful to them? So they teach ROVs, they teach all the multi-beam systems that we just talked about. This is their harbor. Their classroom is right here. And so we have a controlled environment of, probably 25 feet of water here. It's a little shallower on the outside. They dredge it for this training vessel. Those of you might know that this is Great Lakes Naval Training Academy, where they train people to be engineers, ships pilots, and so forth. A great school for that. So, but there's no other school in the world that you can learn the training at this facility. So having said that, I appreciate everybody's time. I know I flew through a lot of things today. There's just so much I didn't touch on that can be involved in stuff like this, but I appreciate everyone's time and patience, and everybody have a great day. I appreciate it.
Thank you, Brian. Such a great
You're welcome.
presentation. We have 4 questions at this point,
Okay.
so she'll give some more people a chance to ask them if they have them. Okay. Do you want to get a drink of water? Because I know you've been talking for a long time.
All
Okay,
right,
you
yeah,
ready?
I'll grab something.
All right. The first question is from Matthew, and he asks, how much data from the water column can you get from different types of echo sounders?
Well, remember, we have to reflect off something. And whether that's a fish, whether that's a piece of wood, piece of concrete and stuff like that, the data generally from water column comes from different, it's more of a chemistry approach. So you've got, if you want to know the salt content, the elements of the water column, pollutants that are in the water column, plant life in the water column, algae, and then the animal life of fishes or turtles or whatever, that comes into a different realm and so forth. The acoustics may pick this stuff up, and actually fish, algae, and stuff are inhibitors of acoustic signal. They'll absorb the sound of it. So you get certain things to let you know that stuff is going on in the water column, but to measure that, to give that an idea of what's going on with the water column, you really don't, unless it's reflecting back, but that generally won't be the water column. Hopefully I answered his question for him. We'll see.
Yeah, if not, just you can ask a follow-up clarifying question.
Okay.
Thank you, Brian.
Yeah.
From Mel, what technology exists to find a hard bottom when disturbed? Fluidized said, okay, let me rewind. What technology exists to find a hard bottom when disturbed fluidized sediment is above it?
Well, that would be a sub-bottom profiling, that you would penetrate that, you would get a different reflection off that, because if it's like a hard packed bottom, like a glacial till or clays or silts or, possible bedrock, you're going to see a different acoustic reflection off that. If it's sands or gravels, you're going to see a different acoustic reflection off that. So you're going to know that if you go down 20 feet, you're going to have a change in deposition there, that you may be hitting a hard glacial till in the middle of Lake Erie. And so you can see that, you'll see the difference in that whole sediment problem. It's one of the issues we look in bridges. On the upstream side of a bridge, we'll get a scour hole starting to develop. But one of the big problems is, as a scour happens when water flows very fast. As water slows down in speed, sediment starts to drop out of the water column into the hole again, reburying the hole. But that hole has lost its bearing capacity. And so if we can run a sub-bottom profiler over that, we'll see the lighter material that was lightly deposited back in there versus the harder compact over, thousands of years of sediment that's down there. So we'll see this harder pack layer with a different reflection than we would with a softer material.
That makes sense. Next question from Conrad. Brian, in shallow water, side scan could hit bottom if it's cable deployed. What is the downside of pole mount? And can you adjust side scan with an MRU?
I have never done anything with a side scan in an MRU. You might be able to do it with it if it was pole mounted. Some people in shallow water use pole mounted side scans to do things with. Nothing wrong with that. Some people, if you have absolutely calm water, some people can turn the side scan on its side, and they can go by a dock or a pier or bridge and image that in the vertical frame. And so, when you're in very shallow water, it is, I would say, 5 to 10 feet or whatever. It's probably better to, if you could pole mount that side scan and use it that way and bring that in, then you can control it. Again, with side scan, you're only as good as your boat captain. So if you can keep away from obstacles and stuff like that, that's probably a good thing. Hopefully, Conrad, I've answered your question. So.
Dual FX single beam would work for fluidized mud. This may be better for dredging works over SBP. Do you agree?
Possibly. I don't know if I can answer that and feel comfortable in my answer. I'm not sure. When you start getting into fluidized muds and so forth, they're huge absorbers of acoustic signals and so forth. I've tried to put stuff down drill shafts before, going into mining shafts that were collapsed and so forth, or mapping tunnels, until that fluid kind of was dissolved into the water column. I wasn't able to get that good of an image. So I'm not sure about that with that type of fluid systems. I'd have to really look at that.
Okay. Is multi-beam preferred over single beam for river bathymetric survey with water depth ranging from 1 foot to 24 feet with high turbidity?
Okay. If you're in 1 feet of water, that's a good way to lose a piece of equipment on a boat. You're going to hit something. And so if you can stick to at least 5 to 6 feet, with single beam, you're only as big as your acoustic footprint. So if you're only, if you're 1 degree beam, your only acoustic footprint may be 6 inches, maybe 4 inches. With multi-beam, you can cover a whole swath. You can cover riverbank to riverbank with that. However, multi-beam's a lot more expensive. There's a lot more tools. There's a lot more things to take into consideration when you start looking at how to get the data. What do you do with single beam data versus multi-beam data is delivering it? Multi-beam data takes processing, computer power. You need to be able to put that into a software that you can kick out a 3-dimensional map of the riverbed. I think multi-beam data is probably better than single beam to make that, to see what's going on with the riverbed and so forth. Especially if you're going long stretches of the river, 1 mile, half mile, 2 miles, 5 miles. So.
Second part of that same question is, are single beam data comparable to that from multi-beam? I feel as though you touched on that, but I don't know if you want to expand just a little bit more.
Well, single beam just means single beams. There's one beam, all right, whether it's an echo sounder, side scan, and we got to know, are we doing imaging or are we doing profiling? If we're doing imaging, single beam is going to take a picture or an image of the bottom. Multi-beam, although that there is multi-beam imaging, but they use multiple beams. You get a lot more coverage, a lot more data, a lot better idea of what's going on, coming at different angles and and perspectives and so forth. So I would say, again, multi-beam is probably a better tool to use, although it's a lot more intense, a lot more expensive to use. Sometimes you have to use what you have, though.
Thank you, Brian. Question from Tim Randall. Great presentation. From your experience, what is the typical ratio of data processing time
Excellent.
to bathymetric collection time for both multi-beam and side scan sonar?
Excellent question. We kind of teach this in our classes. I have, in my years of doing this with sonar work, I have found that for every day of field work, it's at least 2 to 3 days of post-processing. So if I go out and I do, 24 hours or 3 days of sonar work out in the field, it may take, 9 days of post-processing to get that as a deliverable end product to the client. Now, there's a lot of things that you can do. You learn shortcuts, you learn how to do things better, more efficiently, and so forth. But to write a report, to build a mosaic, to give it in a deliverable product to your client, it's 2 to 3 days of post-processing for every day in the field, in my experiences.
Thank you.
Yep.
With sub-bottom profilers, do you get full coverage, or is it like single beam echo sounders where you only get data on a line and there's missing gaps between the survey lines?
Yes. Okay. You will not have gaps in the data if you're pulling it across something. Okay. So if you're towing it, you'll have continuous sonar data, but it'll be a straight line over that. So if you go one direction, then you move to the left 10, 15 feet, you'll have a gap in the data between sub-bottom. So a lot of times what people do, they'll go north-south, then they'll go east and west. Sometimes they'll go on a 45, then try and fill that data gap with everything down there. Yeah, you don't get like 100% coverage, so you can kind of lift it off as individual layers and stuff like this and look at things. But
yeah. Brian, are you aware of any major variations between AUV, not ASV, AUV based sub-bottom profiling versus vessel-based sub-bottom data?
no,
Our data
I did, yeah. Oh, go ahead.
No, go ahead.
No, sorry. I did not speak about AUVs because they're generally for a lot of deeper water work, meaning, 200 feet or deeper, and there's full ocean stuff. But generally the same systems that are used in sub-bottom profilers that you tow or put them on a vessel hull or whatever, they can put in these autonomous vehicles. They're fantastic. They're phenomenal pieces of equipment. They can go down for 48 hours. Kongsberg just came out with what they call their deep water endurance. I think they're talking 72 hours that this thing can go down to like 10,000 feet, stay down there and take side scan data, sub-bottom data, bathymetric data, pictures, whatever you set it up, because it's compartmentalized, and come back to the surface, and it can Wi-Fi you the data, or you can go out, pick it up, download the data, bring the AUV back to the ship, recharge it, and send it back on its another mission. There's shallower water ones that work in 600 feet or less, and there's other ones that work in 300 feet or less. They can use side scan sub-bottom. So you can get the same type of data that you can from the surface towing a piece of equipment or a hole-mounted piece. So,
Shannon, if you have any follow-on questions from that, please re-ask. Moving to the next question, will irregularities in the shape of the seafloor affect how you approach your survey in terms of data collected? Maybe like a coral reef.
Yeah, well, the thing is they will put in inertial navigation systems, and it's all constantly reading its depth. So if it's going up a peak, going back down a peak, because look, there's mountains, as big as Mount Everest down there, and there's all these other types of peaks and valleys and so forth. That's why it's made the job of like ML 370 so difficult. It's because it is such a rocky, mountainous area. But these vehicles of AUVs or side scan or whatever, if it's a towed system, you've got to speed up, slow down, but the AUV will follow the contour of the ground, and it'll just kind of like a helicopter flying 100 feet off the ground. The AUV will do that if you pre-program it for that type of thing. So it realizes, oh, I'm going up, so I need to go up and stuff like that. And I mean, if I have to, and sometimes it doesn't work. Sometimes they hit the bottom and stuff like this. But generally speaking, it'll follow the contour of the ground. So,
Awesome. Thank you.
yep.
How can you deal with gas bubbles coming out of the sediment that may interfere with your scan?
There are times where you have to admit defeat, and if it's constantly coming out, you may be able to map the gas bubbles coming out and so forth. But if you're looking to do things in a larger area, it may the bubbles are a great reflector, so it may hinder your range and an ability to image the bottom. But you'll be able to image the bubbles coming out fairly easy. I've seen that before, where you just image the bubbles, and it's one of those things you just can't really do anything about it. It's just Mother Nature is going to be there for as long as the gas bubbles keep coming. So you can't really do a lot about it. So.
Okay. Is it feasible to perform surveying while active dredging is happening nearby? Or will the noise from the dredge operations interfere with the acoustic signal?
The noise from the dredge should not, unless they're running another type of acoustic signal, like a single beam echo sounder for depth and so forth. But the noise should not be a problem. We should be able to see the bucket go down, grab the sediment, pull it up, the sediment come out of the bucket that's loose and so forth, but it should not have a major effect on the ability to see things. So you can actually set it up a system that's under the barge on a plump weight, and you can image the bucket going out, grabbing things and seeing what's coming and going and where your direction is and any issues or problems that are coming up. I know, especially in dredging, where you have animal life getting involved, like sturgeon or turtles or stuff like this, you can image those stuff to say, hey, maybe you need to shut down for 5 minutes and let the turtles swim by, and then you can start things back up again. So
Makes sense. What are practical depth limitations for various equipment? Are there issues in very shallow water, less than 10 feet?
With 10 feet, there's generally no issues using it. Most equipment on the shelf that you go by is rated to probably 3,000 to 4,000 meters. Is my understanding. Everyone's different. Some equipment maybe only 1,000 feet or whatever, but the manufacturer should have that information for you. Shallow water, the problem with shallow water a lot of times is vessel traffic, producing waves and so forth. Sometimes rain will be a really bad acoustic absorbing thing. Like you expect to go out 100 feet and rain will be hitting the water surface and kind of destroying your record. And generally in shallow water stuff, you have animal and plant life, and they can just pretty much destroy a sonar record. And especially if fish come in trying to look at things, fish are great absorbers of acoustic signals. So, you might have to wait till the fish move out of the area to be able to image something. But generally shallow water, I've done things in, a foot, 18 inches of water and gone out, 25, 30 meter circles and stuff. So I've been able to get really good data if it's nice and calm out and you don't have the plant or animal life interfering with you.
Got it. In respect of everyone's time, I just want to acknowledge that we are right at the end of the webinar. We do have 8 more questions, but I think we can run through these in a couple minutes. Brian, do you mind sharing your contact information in case individuals have follow-up questions on the specific of various systems or the training programs that are available to them? That was a question. So if you don't mind just typing your, or actually I will do that during your next answer. I will share, if you're cool with it, share your contact information.
Yeah, absolutely. Not a problem. I'd be glad to do that for people.
Okay. And then I do want to acknowledge that we did have somebody say that they did have problems getting on. The slides and the recording will be on the website for everybody to download. WEDA members at the end of the month. So I just want to make sure that everyone is aware of that. If you did miss the first couple minutes, we will be able to put that up there. Any recommendation on best?
Catherine, I'll send out an email that has the slides, the presentation on it, and also Brian's contact.
Thank you, Tom. We appreciate you. A couple more questions for you. Any recommendations on best tool to use for seagrass surveys?
Wow. That's a good one. Use generally acoustics, plant life absorbs the acoustic signal. You're going to lose a lot of range and so forth, but it depends on how big the area is. A side scan would be good for, a larger area. If you've got smaller areas, a scanning sonar would probably work better for you, because you're going to be probably mapping more of a blob than you are individual seagrass mounds and stuff like this. But again, with acoustics, sometimes you have to use waffle words. Appears to be, is inconsistent. And the only way to verify that is to either get a camera system, a diver, or some sort of vessel like an ROV or something like that down there to visualize, okay, that is seagrass there, because you won't see the details, I believe, picking up stuff with like grasses and pond lilies and stuff like that can absorb the sound.
Got it. How accurate is sub-bottom profiler when paired with an RTK GPS? And can it be used to replace a single beam unit in a situation when fluidized material or a fluff layer is pervasive in an area where there is limited flushing?
Okay, let's back up a bit. Sub-bottom profiling is a set of frequencies that goes from, say, 2 kilohertz to like 20 kilohertz. It may be higher, maybe lower in certain individual things. That is designed to punch through the sediment layers. All right. So it has their lower frequencies, instead of being the 900 or 1,000 kilohertz, that can punch through the sediment and give us the reflection of that, the different geological units. Silts and clays, generally off the shelf sub-bottom units, you can go 150 to 200, 300 feet down. Sands and gravels, because they're not compact and everything, you may be able to go 50, 60 feet down. So it's ability to punch through that type of stuff. Now with the single beam echo sounder, that frequency is probably generally a little bit higher, and it won't have the pulse to really punch through things. So it's kind of an apple and an orange type of approach. So we're just trying to figure out what the deliverable product will be. Do you need to punch through that? Then you're going to need a sub-bottom profiler with the higher frequencies to do that. Single beam echo sounder is just going to go give you a reflection off the bottom. It may go into the slough material, 2-3 inches, till it hits a harder return than comes back to you and stuff. So it's kind of an apple and an orange effect, but sub-bottom profile would give you the overall picture of everything.
Got it. What are some good resources to learn about sonar data processing?
That's a great question, because there's so many different things out there that people use. There's tons of software that people use, and I don't mean to leave a certain software company out, but you've got software like QPS, Keras, Chesapeake, people use AutoCAD, they use MicroStation, they use Photoshop. It all depends. Yeah, and with the people I help teach with, we've come to the conclusion that the most powerful software out there is really the one you know how to use. And I've seen people get phenomenal data results with off the crap free stuff that, it's like, how did you do that? Then I see people buy the best software out there and they can't use it. And so it's what you know how to use, how to take the process data that you have, put it into a software package that you know how to use to get it to that deliverable point. And yes, there are phenomenal softwares out there. QPS is just phenomenal. Keras, Chesapeake, but there's other software packages out there. Leica has a CloudPoint Cyclone software works that is phenomenal. People don't use it for sonar work. They use it for LiDAR work, but it's still an XYZ data point. It's really phenomenal. So it's what you are familiar with. You might have to step up and learn something new to put your data together to deliver to your client. But, I hate recommending software because there's so much out there that people know how to use and do, and people are developing new stuff all the time. So find one that's decent and spend some time, learn it inside and out, because you'll be amazed what you can put together and so forth.
Awesome. We may have touched on this, so I apologize if it's redundant. But what would be the best technology for collecting bathymetric data for shallow waters 3 to 5 feet deep in a lake environment?
I would recommend kind of like an interferometric system, side scan that's pole mounted, that you can drive that along on a boat. It doesn't have to be a big boat if it's fairly shallow, and you can get bathymetric data and imaging data at the same time. You can put a GPS together. You can, put an MRU if you wanted to on the boat and so forth. But if you're in that shallow of a water, I'd recommend something like that. I wouldn't recommend towing something because chances are you're going to hit bottom or hit something. Not that I've ever lost anything underwater. It's never happened to me. So you just be aware of those things. But I would think some sort of bathymetric system and interferometric that you get both, like the M3 from Kongsberg is a phenomenal piece of kit. You get bathy data, you get imaging data, and you can get all the positioning that you need. And that can be all pole mounted on a vessel and use. So there's a couple right there that you could use. So.
Thank you.
Yeah.
And final question, Brian, you've answered 22 so far. So the final one, lucky number 23.
Okay.
Do you have any experience using acoustic data to locate and monitor vegetation and habitat?
Sure. I live in Michigan in the Great Lakes, and we have been moved on from the zebra mussels to quagga mussels. And they have literally turned the Great Lakes into this Caribbean resort type thing. You can look over, I've been in vessels 30 miles offshore in Lake Huron, and you look over the side of the boat 110 feet down, you see the bottom, you see rocks, you see sand dunes and stuff. These clams and mussels have cleaned up, filtered their original water column chemistry of the Great Lakes, so they're nice and clear. I can show you pictures of shipwrecks that look like the Caribbean that are down on bottom and sand dunes. So yes, you can use that type of equipment to image aquatic life, plant life, and stuff like that on the bottom. If you're looking for, areas that may be, coral, freshwater, deep water corals, whatever it may be, and take a look at that. So yeah, you can do that in shallow water and deeper water. So.
Awesome. Well, thank you so much,
Yep.
Brian. Thank you for staying late to give us your perspective and your lived experience. We are gratefully appreciative of this and the time. And again, you're volunteering to do this. We just sincerely appreciate you. Please, for everybody who's attending, the 150 people that are still online. So thank you guys for staying late with us as well. We do have amazing webinars coming up between now and June, one a month. If you have any ideas for next season, if you will, from September to June, of ideas and topics that you would be interested in, or that maybe your staff needs or your company would like to see happen, please reach out to me. I put my contact information in the chat, and you can get my email. ktomas@animarinc.com is the easiest way, or you can just email Tom. We do have our summer conference coming up in Vegas. That is going to be an extremely well-run event. We are excited about the technical papers that we have been receiving, and you can continue to submit your abstracts to be considered to talk at the WEDA Dredging Summit 23 in Las Vegas. We're accepting those through February 1st. Again, thank you so much, Brian and Tom and Corinne, for coming on board. We appreciate it. And I look forward to seeing everybody next month's webinar and or at the expo coming up this summer. Any final words, Brian?
No, thank you. It's been fun. I've enjoyed it, and I appreciate all the help that you and Tom have done. And feel free to put my email out there if people have other questions and so forth. To yell and scream at me and throw things. Feel free to do that, and have fun and have a great weekend, everybody. Appreciate it.
Yes, I did see that last minute chat requesting PDUs. If you, that information will be sent by Tom here in a follow-up email. So if you have any questions about that, feel free to reply to the email you're going to get from Tom. And again, the slides and the recording are being donated to WEDA by Brian. We appreciate it, and will be posted for members to download and to review at their leisure. Have a great weekend, everybody, and I look forward to seeing you next time. Thank you so much.
Okay. I'll sign off.
Yes, sir.